Welcome to lesson 38 in power system analysis. In this lesson, we will continue our discussion on stability analysis of power system. In the last few lessons, we have been discussing about the rotor angle and stability of the power system, and we had started with the swing equation. Then we talked about small signal rotor stability analysis by linearizing the swing equation. After that, we talked about large signal, that is when we have large disturbances in the power system, how does the system behave. So, we talked about the swing equation and we need to solve this swing equation. Since this is a second order nonlinear differential equation, we try to solve this using a graphical method, which we can apply for a single machine infinite bus system. And in the last lesson, we talked about a method called equal area criterion for studying the rotor angle stability analysis or the transient stability analysis of a single machine connected to infinite bus system. In this lesson, we will continue with that discussion, and we will start with the equal area criterion method of analysis for single machine connected to infinite bus system. Here we will be talking mostly about a single machine which is connected to an infinite bus by means of double circuit line and what happens under different situations. We will take up an example on this, and if the time permits, we will talk about the numerical solution of the swing equation itself. So, instead of using the graphical solution that we can work out for a single machine infinite bus system, we will talk about the analysis where we have number of machines in the system, that is multi machine stability analysis. There we certainly need to do the numerical integration of the swing equation to get the solution for the swing of the various machines. So, we will start with a generator connected to the infinite bus by means of a parallel lines. That is, we have two lines which is connecting this generator to the infinite bus. And in this case, first we will take a case of where one of the transmission line is removed, that is sudden loss of one of the parallel lines. This line can be removed for maintenance purpose, or maybe when a fault occurred or some such situation occurred where we wanted to take this line out. So, suddenly if we remove this line, how the system is going to behave, because when we remove this line, the total reactance, which is or the total impedance between the synchronous machine and the infinite bus will change, and therefore, the power flow pattern will also change. Electrical power output will change because of this situation. So, this is what we have. We have mechanical input P m, which we have said earlier, we will consider it to be constant for the period over which we are doing this analysis. The internal voltage of the machine, that is voltage behind the transient reactance of the machine, is E dash angle delta. X d dash is the transient reactance of the machine. We have two transmission lines, the reactance of which are x 1 and x 2. These in general will be equal, but we can take a case where they can be unequal also. So, we have x 1 and x 2 as the reactance of these two lines, and suppose we want to switch off these lines by opening the circuit breakers at these two ends. The voltage of the infinite bus is V angle 0 degree. As we have said earlier, we assume the angle of the infinite bus to be the reference angle, and the voltage magnitude also most of the time is considered as 1.0 per unit, but anyway it can be any value. So, we have taken here as V. Now, in this system, the power flow when both the lines are working will be given by the voltage E dash into V divided by the total reactance, which is between these two voltage sources. So, into sine of delta angle between these two voltage sources. This is 0 and this is delta. So, the angle difference is delta. So, we have got electrical power output is given by E dash V by x d plus x 1 and x 2 in parallel. X 1 and x 2 are in parallel and this x d is in series with that. That gives the total reactance between the machine internal voltage and the infinite bus voltage. So, we have the electrical power output given by this relationship E dash V by x d plus x 1 and x 2 in parallel, sine of delta, where delta is the angle difference between E dash and V. This we can write as P max 1 sine delta. So, this where P max 1 is equal to E dash V by x d plus x 1 x 2 in parallel. Now, if when the line is switched off, what happens? When the line is switched off, we have the reactance between this voltage generator internal voltage and the infinite bus, that will be equal to x d dash plus x 1 only. So, we will get the electrical power output will be given by the relationship E dash V by x d dash plus x 1 into sine delta, where again delta will be the angle between the internal voltage of the synchronous machine and the infinite bus. We call this as P max 2 into sine delta, because this is the maximum power which can be transferred during this situation where one of the line is switched off. So, we have P max 2 into sine delta. So, what we can do is we can draw the power angle characteristics for both the situation. First situation, when both the lines are in, then we have got the power angle characteristics P delta characteristics of the machine given by this relationship, and when the one of the line is out, we get the power angle characteristics which will be like this. Now, P max 2 is going to be smaller than P max 1, because here we have x d plus x 1 and x 2 in parallel, which is smaller than x 1 or x 2, and here we have x d dash plus x 1. Therefore, we have, in fact, here we should have x d dash, not x d. So, we will find that this, when both the lines are on, the power angle characteristics or the maximum power that can be transmitted will be much more. So, we have this characteristics here, whereas in the other case we have this characteristics. Now, initially the machine is working with both the lines on. In that case, P m is the electrical is the mechanical power input to the system, and the electrical power output under that situation will be equal to the mechanical input, because we have assumed no losses in the system. So, we will have P m is equal to P e, and therefore, the operating point that the system will be working in the initial condition will be this point A, where we have delta 0 as the angle between the internal voltage of the machine and the infinite bus. Since infinite bus voltage we have taken as 0, so delta 0 is the power angle or the angle of the synchronous machine, and this is the operating point. Now, suddenly when the line, one of the line, that is line with reactance x 2 is stripped, then the operating point will shift from this point to this point B, because now the power angle characteristics change, the power flow or the electrical power output is going to change, because the transfer reactance is now different. So, suddenly what we find is the operating point shifts from A to B, and in this case what happens, the electrical power output is much less than the mechanical input, and therefore, we have an accelerating power available, and so delta angle will keep on moving. As when it comes to this point, P m and P e will be equal, but the speed will be somewhat higher than the synchronous speed. So, it will keep on moving like this. So, what we are going to see is that this will keep on moving on this line till the speed becomes equal to synchronous speed at this point, and then at that time we find that since there is more electrical power than the mechanical input. So, there is a retardation which will be taking place, and because of which again delta will start going down. In fact, this line should be at this point. So, finally, what we will find is there is going to be an oscillation of delta angle about this point C. C should be this point. So, this point C, it should be oscillation, and finally, the oscillations will be damped out and it will start working at this point C. And we will see that this area A 1, which is basically the area during which period the rotor is accelerating, and this area A 2, which will be between this C and this whole area, where during which period the rotor will be decelerating, or the decelerating area, these will be equal when we reach this point delta 2. So, this is what we get when one of the line is suddenly removed. Now, suppose instead of working at this point, if we are working at a much higher point, that is the electrical output was more, and initially the PM also would have been more, like instead of working here, if we are working at this point, then what happens? Then we find that suddenly it from A it jumps to B, and then it will start moving. Now, we have much larger acceleration available, or the accelerating area available is much larger, and therefore, the decelerating area must be equal to this, or the decelerating area available must be equal to this or more. Now, if we move it in such a way that this A, B, C area is equal to C, D and this line, that is this hatched area, then what we say is at this point we will have critical stability, or the system will be just stable, because if we work at any point above this, then the decelerating area available will become less than the accelerating area, that is we will have more accelerating area and decelerating area available will be less, and therefore, the acceleration of the rotor will continue, that is we will go beyond this point, and the system will lose stability, that is the rotor will be under a runaway condition. So, this is what we say, that the point at which we can operate, the maximum power at which we can work will be given by this, and the angle D at this point D, which is delta 2, is the maximum angle delta max, and this delta max will be equal to how much? This will be equal to this delta 0 pi minus, sorry, this will be equal to pi minus delta 1. This is the delta 1, and this is pi minus delta 1 will be this. So, we can see what is the maximum angle that can be reached, that is delta 2 under this case. In case we work at a power higher than this, then we are going to lose stability. So, we need to work always lower than this power, and this will be the critical stability point for this situation. Now, let us take another case where we have the same system. Again, P m is the input, E dash angle delta is the voltage behind the transient reactance, x d dash is the transient reactance, x 1 x 2 are the line reactances, and infinite bus voltage is V angle 0 degree. Now, we are assuming a short circuit at one end of the line, say at this end, it does not matter, it can be this end also. In both the cases, when a short circuit occurs on the line which is very near to this bus, then what happens is the voltage of this bus is also equal to 0, and under such a situation there can be no power transfer. Same case, if the fault occurs very near to this bus, at this end of the line, then also the voltage of this bus becomes 0 and there will be no power transfer which will take place under such a situation. That is, we have shown this situation when we have a fault at this end of the line. So, on any one line, if the fault occurs just near the bus, then the voltage of this bus is 0. This is what is shown. So, voltage at this bus is shown as 0, it is grounded, and therefore, there will be no power transfer which can take place under such situation. And that means the during fault period, the electrical power output of the machine will be 0. And after this, if we switch off this line, that is this fault which has occurred on this line at this end will be isolated by opening of these two circuit breakers, because this fault will be sensed by the relay and the relay will send signal to the circuit breakers at these two ends to open, and therefore, the fault will be isolated by opening these two circuit breakers. In that case, again we have a system where we will have x d dash and only one of the line working instead of both of the lines working in this situation. So, we have initial case, we have both the lines working. So, the electrical power is given by the relationship E dash V by x d dash plus x 1 and x 2 in parallel into sine delta, that is what we write as P max 1 sine delta. In the case when the fault is on, that is during short circuit period, we have electrical power output is equal to 0, that is P electrical in the second situation, that is when the fault is on, in that condition is equal to 0. When the fault is cleared, then the electrical power output is given by the relationship P E 3, that is after fault clearance or post fault situation is given by E dash V by x d dash plus x 1, because the other line has now been tripped. So, this into sine delta, which we call as P max 3 sine delta. So, we can again draw the power angle characteristics under all the three situations. So, the first one is the pre-fault condition, the initial operating condition, which is given by this P delta characteristics. Second condition, when the fault is on, is electrical power output is 0. So, it is this horizontal line which defines that situation. The third one is when one of the line is out, and that is given by this situation. So, we have here P max 1, which is pre-fault, this is during fault, and this is P max 3, which is defining the post fault condition. So, pre-fault, during fault, and this is the post fault condition. Now, initial operating point, we have P m and P equal. So, the angle at that point we say is delta 0, that is here P electrical will be equal to P mechanical input. So, it will be given by this operating point where the angle is delta 0. When the fault occurs, the electrical power output becomes 0. So, the rotor angle will start traversing on this, because electrical power output now is 0, and suppose it has reached point delta 1 when the fault is cleared. When the fault is cleared by opening the circuit breakers, now we have only one line acting or one line working on the system. So, suddenly the operating condition will now jump from this point to this point, and we will have again delta moving along this characteristics, which is the characteristics for post fault condition. So, what we have during this period, we have acceleration, and the accelerating area all through this period, the accelerating power is equal to P m, because P e is equal to 0. So, P m minus P e is equal to P m in this case. Suddenly, it will jump to this point where the electrical power output will be governed by this characteristics. So, at delta 1 it has jumped here. So, in this case we have deceleration. So, the rotor will start decelerating, but since its speed is more than synchronous speed, it will still keep moving. When it reaches this point delta 2, then the speed becomes equal to the synchronous speed, but since the mechanical power input is less than the electrical power output. So, delta will keep on moving along this, and what we will find is finally it will start operating at this point where P m is equal to P e. So, at this delta angle it will start working finally, because the oscillations will die out. Now, when we see this whole area is the area during which there is acceleration of the rotor, this area, that is between P m and P e, this curve that we have is giving us the decelerating area, and we will get this when A 1 is equal to A 2 at whatever point, that is at point delta 2, then we will have reached the synchronous speed at this point. So, what we find is the accelerating area and decelerating area must be equal. Now, suppose instead of working at this point, if we would have worked at a little higher point here, that is electrical output being a little more than what it was earlier. So, P m also would have matched that point and we would have been working here, then in that case we would find that accelerating area will increase and the decelerating area will reduce somewhat, but the maximum decelerating area is available is above this line and below this curve. So, that is up to this point delta max, which again will be equal to pi minus this angle that we have. So, pi minus this angle will give me this delta max, and that is the maximum point up to which we can work. So, that will give me the critical angle. With the same thing we can see, instead of tripping this line when we have reached delta 1, if we tripped it a little later, that is if this delta 1 was here, then again what we find is the accelerating area will increase up to this point and decelerating area available will be only up to this much. That is, if this area becomes equal to the area here, then we will have a critical stability, and then that angle at which we have cleared this, where this A 1 is equal to the maximum decelerating area available, will be called the critical clearing angle for this situation. So, we can have this critical stability depends on two things, that is the initial operating point and when we are clearing the fault. So, the faster we clear the fault, smaller is the accelerating area available and more is the chance of system remaining stable, because you have larger decelerating area available. If you clear your fault later, suppose we clear it up to this point, then the accelerating area available will be coming up to this point and decelerating area available may not be enough, that is A 2 may become the maximum A 2 which is available may become less than the accelerating area which is there, and system may become unstable. So, if we keep on increasing it slowly, we will come to a point where the accelerating area A 1 is just equal to the maximum available decelerating area under that condition, and that point or that angle we call as the critical clearing angle. Now, let us take another situation where the fault occurs somewhere in between in the line. In this case, we have considered a situation where the fault has occurred at the middle of the line, but it can be anywhere in the line. Only thing which is there is, initially when there is no fault, both these lines are working and the system has the electrical power characteristics given by E v by x d dash plus x 1 and x 2 in parallel into sin delta. That is what we get. When a fault occurs here and this is cleared by opening of the circuit breakers at the two ends, then again we have the power transfer given between the machine and the infinite bus is again given by E dash v divided by x d dash plus x 1 into sin delta. That will be the post fault condition. During fault, in this case when the fault occurs not at either end of the line, but somewhere in between, we are going to get some amount of power transfer which is dependent on what is the transfer reactance under the faulted condition. That is, with fault on here, what is the transfer reactance between this point and this point. This we can find out. That is, if we see, look at this circuit condition, we have x d dash and this x 2 by 2 connected to the ground, and this x 2 by 2 connected to the ground, and this x 1 between these 2 points. So, this is the situation, x 1 between these 2 points, x 2 by 2 connected to the ground, x 2 by 2 connected to the ground here. So, this forms a delta x 1, x 2 by 2 and x 2 by 2, and we can always use star delta transformation to transform it into a star, where we have the star impedances given as x a, x b and x c. That is, for this delta that we have, we can convert it into a star equivalent star, and the impedances for that equivalent star will be x a, x b and x c. So, under this situation, the circuit will look like this, x a, x b and x c here, and we have now x 1 and x a in series here, x b on this side and x c here. Now, again this looks like a star, and this star can now be converted into another delta using star delta transformation, and then we will get this as x 2, and this is an impedance here, this is another impedance here. Now, these two impedances, since they are across the voltage sources, they do not have any effect on the power transfer which takes place between this and this. So, this is what we get as the transfer reactance for the system. So, what we need to do is find out this x 2, and in this case we will get the value of power transfer will be given by E dash V divided by x 2 into sin delta. So, now we have 3 parts. First part is pre-fault, which is E dash V by x d dash plus x 1 and x 2 in parallel. So, that is the pre-fault power angle characteristics that we have. Then we have during fault characteristics, which is given by E dash V by x 2, that is this divided by x 2 into sin delta. So, this is the during fault characteristics, and when one of the line is removed, then we have E dash V by x d dash plus x 1 into sin delta. This characteristics is given by this post fault characteristics here. So, we have P E 1, P E 2 characteristics, that is during fault, and P E 3 characteristics post, which is post fault. Now, initially the system is operating at this point where P m is equal to P E. A fault occurs, then suddenly the operating point will shift to the during fault operating characteristics at this point. Since we have more mechanical power input and less electrical output, the generator rotor angle will start accelerating. So, rotor angle will keep on increasing. Let us say at this point we delta c, we clear the fault. Then once we clear the fault at this point, what happens? The operating point will jump to the post fault characteristics, that is up to this point, and during this period the accelerating power available at each of these points will be between this P m and this characteristics, that is the during fault characteristics. So, this is the accelerating area which is available, and once we have gone to this post fault condition, we are finding that the electrical power output is greater than the mechanical input. So, we have deceleration. Of course, rotor angle will keep on increasing till the speed is, because of deceleration, reaches back to the synchronous speed. So, which happens say at this point delta 2. So, we will get the decelerating area, which will be between this Pm and under the post fault curve here A2. So, when these two are equal, we will get the final operating point here, that is delta will move from here to this, go up to this point, that is start from here, jumps here, moves like this, goes here, goes up to here, and then it will keep on oscillating about this point, and finally it will work on this point. So, this is again, if either we clear it a little later, then what happens, the area A1 will increase and the area A2, the maximum available, will be between this curve and this Pm, that is up to this point. So, this can shift only up to this point. So, if we clear this fault a little later, A1 will increase and A2 will keep on reducing, that is the available A2 will keep on reducing. So, when this A1 is just equal to A2, available A2, we have the critical clearing of the fault. That is, if we clear our fault before that delta clearing, that is critical clearing angle, then the system is stable. If we clear the fault after the critical clearing angle, then the system becomes unstable. So, that is the situation that we get. Now, we can always find out what is the critical clearing angle. Let us see how we do that. So, this is what is depicting this situation. This area A1 increases also if our initial operating point is higher or if our clearing angle is larger. Now, in this case, we see this A1 is just equal to the maximum available A2, and therefore, we call this as critical clearing angle. Now, how we find this critical clearing angle? Again, what we need to do is calculate these two areas, that is the maximum available decelerating area and the accelerating area up to the clearing time, and when we get this, equate these, we will get the value of the clearing angle, and that clearing angle we call as the critical clearing angle. So, let us see this situation, that is initial starting point is delta 0, the fault is cleared at delta Cr, and we have delta 2 which is equal to delta max in this situation. So, what we have is the accelerating area is equal to Pm minus P max 2 sin delta, that is Pm minus P max 2 sin delta, this is this characteristic. So, above this, all this area that we are talking about. So, Pm minus P max 2 sin delta d delta integrated from which point, delta 0, from this angle up to this angle delta Cr. So, delta 0 to delta Cr. So, this is the integral that we have, and this must be equal to how much, the decelerating area which is available. So, decelerating area which is available is given by integral from delta Cr to delta max of Pe3, that is this Pe3 sin delta minus Pm, that is this area will be area under this curve and this line, that is area below this curve and above this line. So, this is what we are writing here, from integral from delta Cr to delta max P max 3 sin delta minus Pm d delta, that is P max 3 sin delta is giving this characteristics minus Pm. So, we have got this as the decelerating area, maximum amount of decelerating area available, because delta max we have used. Delta max is equal to pi minus sin inverse Pm 1 by P max 3, that is delta max is going to be equal to pi minus this angle, is not it? This is the angle where it is going to work, and this angle is equal to how much? This is electrical output, in this case is going to be equal to P E3 PE3 sin delta, and we have the mechanical input which is equal to PM1 into sin delta 0, that is this point. So, using this we get delta max is equal to pi minus sin inverse PM1 by P max 3 or P max 1 by P max 3. So, this is what we get as delta max, because we have pi minus delta max is equal to sin inverse P max 1 by P max 3. So, putting for this, we integrate this, we get Pm, which is a function of delta, Pm into delta, I am sorry, this delta should not be the in subscript mode, this is Pm into delta, because we are integrating this, plus P max into cos delta, sin delta, when we integrate this becomes minus cos delta, this is minus. So, plus P max 2 cos delta from delta 0 to delta critical, delta 0 to delta critical, plus we take this on this side, then we will have this as minus term. So, minus when we integrate this sin delta will become minus cos delta. So, this is plus P max 3 cos delta, plus this is minus when we have taken on this side, this becomes plus. So, plus Pm into delta. So, this also should be Pm into delta from delta critical to delta max. So, we substitute these values. So, we will get Pm delta critical minus delta 0, that is Pm into delta, we are writing Pm into delta critical minus delta 0 when we substitute the limits, plus P max 2 cos delta critical minus cos delta 0, plus P max 3 cos delta max minus delta critical, sorry, P max 3 cos delta max minus cos delta critical, and plus Pm delta, which will be Pm into delta max minus delta critical, Pm into delta max minus delta critical, this will be equal to 0. So, now substituting the values, we can finally calculate cos delta critical is equal to Pm delta max minus delta 0 minus P max 2 cos delta 0 plus P max 3 cos delta max divided by P max 3 minus P max 2. So, this is after simplifying from this, we can get cos delta critical as this expression. Now, this angle that we will get from here will be in terms of radians. If we are using degrees, then we will have to multiply then we will have to multiply it with 180 by pi. So, cos delta critical, in that case if we are using delta max and delta 0 all these as degrees, then we have to multiply them, convert them into radians. So, it will be pi by 180, we multiply them and we get this value. So, when we are using radians, we are using like this, when we are using degrees, then we have to multiply or convert them into radians. So, this is how we can calculate the critical clearing angle. Now, as another situation which comes many a times is the circuit breakers that we have for the circuit breakers that we have in the system many a times have what we call recloser or automatic recloser. That is, these circuit breakers, because most of the time the faults which occur on the power system are transient in nature. That is, once you clear them, if you again close the line, things will become normal. That is, so a fault has occurred, and if we clear the fault and after that if we reclose the circuit after a short time, then the circuit will be in general normal. And this operation we call as the recloser of the circuit breaker. Now, if that is the situation, that is, a fault has occurred on this line, let us say, and we have opened the circuit breaker, then we have only one line left in that case, but after some time if we reclose and the fault has been cleared, then both the circuit will be on, and so the power angle characteristic will change to pre-fault condition. However, this recloser has certain disadvantages also. Under certain situations, this can create more problems, because if the fault was not a transient fault, that is, it was a persistent fault, then if we reclose the circuit breaker, we will be closing it on the fault. So, instead of going to the pre-fault power angle characteristics, that is the electrical power output, will now depend in this situation for the power angle characteristics, which is given by the faulted condition. That is, if we reclose on the fault, then again we are going to the faulted condition. So, instead of going to the pre-fault condition, we go back to the faulted condition from the post-fault condition. So, this situation is shown here, that is, we are initially operating at this point, which is the pre-fault power angle characteristics, with P m is equal to P e, and the angle is given by delta, that is delta 0, because P m is equal to E dash V by x d dash plus x 1 and x 2 in parallel into sin delta 0. So, this is delta 0 at this point. Suddenly the fault occurs, then say in the middle of the line or somewhere, then based on the transfer reactance between the infinite bus and the generator, it drops down to the post fault condition. So, post fault characteristics. So, suddenly it will drop down here, delta angle will keep on increasing because of the accelerating power available. We clear the fault at this point, then suddenly it will jump to this point, and we will have this moving, I am sorry, this whole area should be hatched like this, not from here, but it should be from here. So, this A 2, that is this point should be here, I am sorry. So, this point should be here. So, this whole area from this point up to this should be hatched. So, here we have moving on this point, and suddenly at when it has reached this point, if we reclose the circuit breaker, then if the fault has been cleared, the operating point will jump to this point, and it will keep moving like this. Now, in this situation, what we find, if the fault was a transient fault, then what we are seeing, the decelerating area available will be much larger. It will be like this area which will be available, because now the operating point will be on this characteristics. But in case the fault was persistent fault, then from this point operating point, it will suddenly drop to this point, rather than going up, it will drop here, and we will have more acceleration available, and the system may become unstable also in such situations. So, normally in most of the situations, we allow 1 or 2 reclosers, and after that the circuit breaker is locked with its contact open. Otherwise, what happens is that it may lead to instability in the system. So, again in this case, if we are assuming it to be a transient fault which is cleared, which is most of the time, then we can find out the accelerating area available, that is the accelerating area up to the clearing time, and the decelerating area available will now be given by this. So, if recloser occurs at delta C r, then suddenly the operating point jumps to this point, and the available area, decelerating area available will be given by this. So, again we can calculate that in this case delta 1 is equal to delta max, that is pi minus delta max. Here this delta max which is available will be here now, and so in this case this will be equal to pi minus delta 0 as such. So, if we look at the accelerating area, it is from delta 0 to delta clearing, P m minus P max 2 sin delta d delta, that is P m minus P max 2 sin delta, this area from delta 0 to delta C, this delta clearing, this is what we get. And then the decelerating area available from delta CR to delta C to delta CR. This should be delta C and this should be delta C to delta CR. Here this is from delta C to delta recloser delta RC, not CR. So, delta C to delta RC P max 3 sin delta minus Pm. This is the part that we get up to this point, that is this area, and from delta RC it jumps to this point. So, we have plus delta RC to delta max P max 1 sin delta minus Pm, that is now the operating characteristics is given by this. So, P max 1 into sin delta is coming minus Pm minus this. So, from here this area will be available for deceleration. So, this area is what we are talking about here, delta CR to delta max. Now, again using this we have, this should be delta clearing, delta C or delta CR, it does not matter. So, here we have delta 0 to delta CR Pm minus P max 2 sin delta, that is here I should write delta CR instead of delta C. So, this what we are trying to do is trying to equate the accelerating area with the available decelerating area, and using that we can calculate the critical clearing angle or the recloser time required. Now, let us take one small example for this. Again here what we have, a single machine connected to an infinite bus by means of a double circuit line. The fault occurs at the middle of the line. For the system shown in figure, both the terminal voltages and infinite bus voltages are 1 per unit and the generator is delivering 1 per unit power. Calculate the critical clearing angle and the critical clearing time. Of course, critical clearing time in this case we cannot calculate when the system is subjected to 3-phase fault at point P, that is middle of the line as shown in figure. H for the synchronous machine is given as 5 megajoules per MVA. Now, here if we see the XD dash for the generator is given as 0.15, the transformer has a reactance of 0.1 per unit, the lines have reactance of 0.5 per unit. So, pre-fault operation what we have been given here the terminal voltage and infinite bus voltage are 1 per unit, that is the voltage at this point is given as 1 per unit. The voltage behind transient reactance we do not know. So, we need to find that out. So, first thing is what we will do is we will try to find out the transfer reactance between this point and the infinite bus. So, the transfer reactance between this point and the infinite bus is J.1 plus these two in parallel. So, this becomes J.25. So, it is J.1 plus J.5 divided by 2 lines in parallel, this is J.35. So, what is the power angle characteristic that we will get? P is equal to using this relationship we will be able to find out what is the value of the power which is flowing, and therefore, after that we will be able to find out the voltage behind the transient reactance for the machine. If we calculate that, it comes out to be 1.038, and if we use this relationship, then P is equal to 1.038 into 1.0, and the total reactance that we will get here will be this 0.15 plus J.1 with this 2 in parallel. So, that is going to be equal to 0.5. So, 1.038 into 1 divided by 0.5 into sin delta is equal to 2.076 into sin delta. Now, since we have been given that P, that electrical power transferred is 1 per unit. So, using this as 1 per unit, we will get delta 0 as 28.786 degrees. Now, when the fault has occurred at the middle of the line, again we have the circuit relationship like this. E is given as 1.038. This is the transient reactance, this is the transformer reactance, and this is the line 1, and this is the other line where the fault has occurred at the middle. Now, what we have is we have this delta formed, which we can convert into a star. So, if we do that, then we get this as 0.125, 0.125 and j 0.0625. So, this is the star for this delta. So, this j 0.1 is the transformer reactance and this j 0.15 is the transient reactance of the machine. So, now this is the circuit that we have. So, we add this up 0.25 plus 0.125. So, 0.375, j 0.15 and j 0.625. This forms now a star circuit, which we can convert to a delta. If we do that, then we have got the transfer reactance here as j 1.2496. So, this is now the transfer reactance between this voltage behind the transient reactance of the machine and the infinite bus, and therefore, we will have the power angle characteristics for the faulted period given by P E 2 is equal to 1.038 into 1 divided by 1.2496. This is the reactance, this is the E dash, and this is V into sine delta. So, this comes out to be 0.8306 into sine delta. When the fault is cleared by opening the circuit breakers of the two ends of the faulted line, then we have the system like this, where this is the transient reactance, this is the transformer reactance, this is only one line now j 0.5, and this is the infinite bus. So, transfer reactance in this case comes out to be 0.5 plus 0.1 plus 0.15. So, j 0.75. Therefore, P E 2 is equal to 1.038 into 1, this is E dash, V divided by 0.75 into sine delta. This comes out to be 1.384 sine delta. So, we can draw the three characteristics, pre-fault characteristics, which is given by 2.076 into sine delta, during fault characteristics, which is given by 0.8306 into sine delta, and post fault characteristics, which is given by 1.384 into sine delta. So, this is P max is 0.836, this is 1.384, and the initial one is 2.076. So, 2.076 is the maximum power here. So, we get these three characteristics. Now, we have a initial operating point here, which is 27 degrees, and the fault occurs, the operating point jumps down to this point and it accelerates around this. When the fault is cleared at this point, it will jump here and it will move around this. Now, if this point of clearance is the critical clearing time or critical clearing angle, this delta CR, then this total area, which is the decelerating area, must be equal to this area, which is the accelerating area. So, again using the same relationship that we had developed earlier, delta max is equal to pi minus sine inverse P m 1 by P max 3. So, this is pi minus sine inverse 1 by 1.384, which is equal to 2.334 radians. That is, here delta max is 2.334 radians. That is what we have got, and the area A1 is equal to P m minus into delta CR minus delta 0 minus integral delta 0 to delta CR P E 2 sine delta d delta. That is, we are saying this rectangle, which is P m into delta 0 delta CR minus delta 0. Subtract from this area below this curve, which is again from integral of deltas from delta 0 to delta critical of this characteristics. So, we are writing this P 2 sin delta d delta. Okay. So, this is the accelerating area that we have. So, we substitute the values here, then we will get this as 1 into P m is 1, delta critical minus delta 0 is 27 degrees. So, this is minus 0.5024 and this P 2 is given as 0.8306, and with this sin delta d delta, when we do with the substitution of the limit, this is cos delta 0 minus cos delta CR. So, we substitute these values, then we get this as the area, which is the accelerating area. Similarly, we will get the decelerating area A 2 as delta critical to delta max P 3 sin delta d delta minus P m delta max to delta critical. That is, from this point we are saying the area under this curve from this point to this point minus the area, rectangular area here. So, that is what we are writing here. So, P 3 sin delta d delta from delta critical to delta max minus P m delta max minus delta critical. So, substituting the value, this comes out to be minus 1.379 plus delta critical plus 1.384 cos delta critical. So, equating these two A 1 and A 2, we get this relationship, delta critical will cancel out, from which we will get 0.5534 cos delta critical is equal to 0.149, from which we will get cos delta critical is equal to 0.2692, and from which we will get delta critical is equal to 74.38 degrees. So, this way we can calculate the critical clearing angle. So, this is how we use the equal area criterion for transient stability analysis of the system. In the next lesson, we will talk about the numerical integration of swing equations and how we use it for multi-machine system stability analysis. Thank you.